start today's discussion. So what I'm going to do today is review a little bit on device physics, on understanding how a transistor, bipolar junction transistor functions, and the key mechanism as to why does this control why does we establish the third terminal control. As I said, the main purpose of having a transistor is to create a third terminal control. So we're going to talk about that in more detail. And then the next thing we're going to do is, of course, having a basic understanding and a basic current model. How does one apply this current model into a circuit analysis, and how does one use this to generate, for example, small signal models and then some circuit examples. So we're going to actually go into circuit example and then come back to other detailed problem with devices. So the basic idea is that we have already introduced the basic operation of an NPN transistor in active mode. So we're going to use this to go through the basic operation. As I said, for NLOP application, NPN transistor in active mode is the most useful structure that you will use for amplifying signals. So we're going to talk about the application in circuit in a little bit, and then come back to revisit the device's more complicated operation. For example, what happened when you reverse bias, what happened in PNP, and what happened if you in saturation mode. So we're going to first focus on active mode because this is the most important operation mode that you're supposed to place your device in when we're amplifying signals. So if you remember, we talked about a NPN transistor. As I said, there's emitter NPN, once again NPN. The cross-sectional view of NPN looks like that. And then we analyze the three parts of the current. So first of all, you have to understand that the key current we want to control is the collector current. The reason for this is that this is typically the node if we're amplifying. So that's your output. You want to make sure that your output current is well controlled. So we want to talk about what is how does one control this particular output current, which is the collector current. So the first understanding is that if we're operating in active mode, I want to emphasize once again, this is the most important operating mode you're supposed to place your circuit in if you're operating as an amplifier. So we're going to talk about under active mode. What happens is that your base region will then create we will create a higher concentration at the EB junction and lower the concentration at the BC junction. So this is where your input, you lower the barrier, 4 bias BN junction. So with 4 VBE, and then VBC is, so if you look at NP, B are always N and P. So that's, let me highlight this. This is NP, P. So if you plot a diode, this is 4. This is it's a back-to-back control diode. Sorry. It's a PNP. So I'm drawing an NPN. So NPN. So you want to forward bias this B junction, reverse bias this junction. There's 2 junctions, right? So you forward junction to allow lower barrier, allowing diffusion to happen. So a lot of magnetic carrier coming from emitter will then go into the base. And then we create this profile, we create this gradient, dNdx, large dNdx, allowing the electrons to come through and then being collected by the collector. So we use a depletion region to collect the collector. So one of the key understanding I want you to remember is that the collector current, even though it goes through and comes from if you think of yourself as an electron, you come from emitter through drift, diffusion, drift, okay? But what is limiting your overall current is what we are concerned. So what is your bottleneck in this travel will then determine the overall current. So this is determined by minority carrier, which is electron in this case. Minority carrier meaning minority in base. which are electrons, and diffuse. Make sure that it's diffusion limited. It's a diffusion limited current. You look at where your limits are. So diffusion limited in base. So one of the keys that minority, once again, is minority carrier. I want to highlight it's minority carrier in base is electron through diffusion in base. Because its limitation, your bottleneck is the base in collecting collector current. Therefore, if you look at the current itself, the current will then proportional to base structure, right? Remember, it's inverse proportional to the total number, or I shouldn't say total number, but the unit area number of dopant in base. So this is the number of dopant in base. If I time AE, that will be a total number. So it doesn't really matter. You can cancel it. So that's the number of dopant in base. Right? So base structure, that's the key I want to mention again. Collector current depends on base structure. And of course, carrier. Nu1 is because it's electron. So this N comes from the reason its minority carrier is electron. Okay? So I can also make the same statement for IB. But what happens to collector current? Collector current is determined, the same thing, determined by minority, also minority carrier, because bipolar junction transistor is a minority carrier dominated device. It's all governed by diffusion. Because I'm lower the barrier. Minority carrier here is an emitter. Right? Remember, this is the whole current. And because emitter is n-type, therefore its minority carrier is whole. Right? The main difference is that. And it's also controlled by diffusion. So the statement is the same, only is a different structure in emitter. So IB, as I said, is whole current. It's limited by whole current injected into emitter. Therefore, emitter structure will limit how many whole current, the level of whole current that can be established under this 4-bias condition. Therefore, you will find that IB will then be proportional to emitter structure, as I said, will be depending on emitter doping constant, inverse proportional to emitter concentration and diffusion inside emitter. And because it's whole, therefore you will see mu p. The reason why for this is that it's mainly whole current, consists of holes. It's whole current. Okay? So the basic understanding will allow us to conclude that we know that one of the key parameters other than the 4-bias characteristic, we already know that collector current depends on IS exponential VBE over VT, where IS will be inverse proportional to MBWB, as I said, mu n. We already know that. Because these are the, and of course area, something like that. You can go through the detail, I'm not going to write down, but proportionally, what it depends on is device structures are inverse proportional to the base dopant amount, and of course, directly proportional to cross-sectional area. AE, once again, this is the cross-sectional area of a BJT, I should say active area, cross-sectional active area of the BJT. If you look it up from the top view, it's defined by the emitter area because that's defined at last, right? So then the next thing is that, so one of the key parameters I want to highlight again is IS. Okay? So this will allow us to establish, what does this allow us to establish? If you think about it, if I want to construct my bipolar junction transistors model, I want to look at the output terminal, which is IC, and input control. So based on this model, I could actually establish a sub-circuit model. If you use circuit theory, it will look something like this. I already established something we started with, we wish on our wish list, which is what we want to have is a voltage control current source. If you think about it, if I'm applying, if this is my base, this is the emitter. We're not going to go into detail, but first order, if you look at this equation, what we have already established, if I'm connecting my circuit this way, and the voltage across VBE is, we define it as V1, then the current, the output current, this is my output current IC, which will then depend on IS exponential BT V1. Okay? So this is voltage control. You already established a third terminal control, VCCS, right? So this then tells us a very important thing. If you actually express this in a schematic in terms of IV characteristic, what does it mean? It means that your output current, which is, this is my output current IO, which is IC. I want to plot IO as a function of V1. I'm actually getting what? As a function of VO, sorry, VO. For this particular circuit, if I'm defining, this is a little busy. If I'm defining this terminal, sorry, this terminal as my output terminal, so I'm concerning at this particular terminal, if I'm wrap it with a black box, I wanted to observe what is the corresponding response. For example, I'm applying a voltage across, which is VO. I'm observing its output characteristic. This is the output characteristic of a transistor. This is typically referred to as the output which is IO versus VO. So what do you think it will look like? For a given V1, it should be a flat line because it should be independent. Remember, this is a current source, which is third terminal control. So if it's an ideal current source, what it means is that it will deliver a constant current independent of output. This is what we want. We want a voltage control current source, which is independent of the stress across, the voltage across the output terminal. So I could provide constant current with the control, the input, rather than the bias on the output. Okay, so this is the ideal that we wanted to achieve. So we actually got it. So you got a flat line. So this is under, for example, V1 equals to maybe 0.8 volt. I might get a V1 equals to 0.85 volt. So you will see something more like this. It will be a flat line. It will indicate a different IC, maybe IC1, IC2. So that's how you see a voltage control current source. V1 control, in terms of circuit, it's a V1 control current source. It should be flat. This line doesn't look supposed to be flat. That's an ideal. Flat suggests that you have an ideal current source, right? For an ideal current source, it should be flat. So ideally, a transistor should be able to deliver a third terminal control output current, looks something like this. And based on our first order model, we already established that, right? So if you think about it, what happened when I increase VO? Why is it flat? normally what happens is that you apply a voltage, for example, your 4-bias PN junction, the current itself will be depending on your voltage, right? When you change your voltage, you get an exponential. More the other side, it's very, very sensitive current voltage relationship. But how does it desensitize output? You want to think about it. Where does this additional voltage go? We're going to talk about it when we talk about non-ideal case, but you get a sense as how does this being established, there's a key concept behind it, okay? So once we have this, the next thing we talked about, other than this current, this is the first key important result, one, which is 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 the key parameter. The other key parameter in describing a transistor is second important parameter, which is current gain. Remember current gain, which is beta. So beta current gain is, this is also the key parameter, will be a device parameter which will be given to you. So two key parameter, one is IS, which describe the 4-bias PN junction components. It's very similar to a diode, but just taking out one part of the electron. So we know that because from our last discussion, we know that when you 4-bias PN junction, the diffusion of holes and diffusion of electrons raise exponentially together. Therefore, the only concern we want to establish here is the ratio between the two. So the beta current gain in a bipolar junction transistor is defined as the ratio between so this is the same as the emitter current and hole current in a so this will correspond, IE will correspond to the electron current, the hole current in 4-bias in B junction. So this is the same as when you 4-bias a PN junction, you take out the electron part, the hole part. The total will be your emitter current, the total diode current, which is actually the emitter current. We'll talk about that a little bit. But then you separate the two. So the collector current will be sucked up by the electron current. The electron diffusion current will be sucked up by the collector. Therefore, the ratio between the two is just simply look at the 4-bias PN junction and its electron hole current ratio in a 4-bias PN junction, which is the B junction. So we already know that based on our analysis, electron current or collector current is proportional. Let me write it again, mu n. Key parameter is whatever inside base. We also know that our emitter base current, is proportional because it's a hole current. So it's mu p NEWE. Therefore, you can get your beta, depends on device structure, NB, sorry, you flip it because it's in the denominator, so it's NEMB, WEWB, mu N, okay? So that's the current gain of the circuit. We already talked about that a little bit. So once we have these two parameters, we should be able to define when you apply this. The last thing is I want to mention once again. So what about emitter current? We already addressed collector current, base current. You can defer. You could defer base current based on getting a current gain. So once I have the circuit, once I have this model, I already established that base current and collector current are against the ratio. So what is next is that if you look at this, so remember I have base current going in. Even though electron is going in this direction, collector current is going down. because my electrons are moving from here to here. So collector current is going down. Therefore, based on KCL, we should know that this current, your emitter current, should be the total diode current. So emitter current IE is equals to the electron current, collector current, hole current, base current. Okay? So this is very simple. We know that there's a difference between the two. So there's various ways of finding out emitter current, which is 1 plus beta IB, or in terms of 1 plus beta collector. So either you start with the base or you start with collector current. So once you find the collector current, you can use this equation to find the emitter current, or you can find the base current. The relationship is the same. So as I said, this is typically referred to, beta is typically referred to as the current gain or common emitter. It's called a common emitter current gain. The reason why it's called common emitter current gain is that if I put this to ground, this will be my input, this will be my output. So input output will be defined by the input output current ratio, will define the IC over IB. So another way of doing this is that if I'm treating emitter as my input, if I'm putting this to ground, this would then be my input. So there's another gain called common, use another color. So we define something called alpha, which is you're assuming emitter as your input, and collector is also the output, but you use the emitter as it. So when you're using this as your input, this will be ground. So this will refer to as the common base structure. We're going to talk about that a lot when we talk about, I should say, amplifier architecture. So this is a type of amplifier architecture. So common base current gain. Well then, because the base is being common, therefore you look at input and output. This would then become your input. Collector is still your output. So what do you think this should be? This would then become 1 plus beta IB. This is beta IB. So if you put them all in ratio of IB, this will be equal to 1 plus beta beta. So there's typically two ways of expressing your current gain. One is through a common emitter structure. Then you will see the ratio between your input, which is base current collector current ratio, which is called beta. And these are typically the key. And if you're doing it in a different, if you're operating your transistor in a different direction by commenting this base terminal, then this would then be referred to as a common base current gain. So for alpha, an ideal structure is alpha is close to what? If I have a high beta, alpha would then close to what? Correct. So for most cases, if beta is larger than 1, what happens is that alpha will be approaching 1. Meaning that whatever you're putting in will be delivering out. So that will be a current buffer. So what you want to establish in a common base structure is a current buffer. So once you have this understanding in its definition and its characteristic, then you will know why people are operating these circuits under different modes, okay, or biasing condition for delivering different functions. Okay, that's good. So what we're going to do is now, once we already have these understanding or model, so let me emphasize once again, two important parameters, IS, device parameter IS, VB, or there's two, let's just say the device model. So for device model, of a, let's just limit ourselves to NPN transistor. I want to emphasize, and this is only true when an NPN transistor in active mode. This is the same as you can only use the exponential model when the diode is 4 bias. In reverse, you're just assuming that the diode model actually works for reverse, but I'm just saying that the model, this model only works when you're operating in active mode, which is, once again, I want to define it again, which is I'm assuming my VBE is larger than 0, 4 bias, VBC is smaller than 0. This is roughly determined that it's in an active active mode. So you have to make sure that you're operating in that, then this model can be valid. Okay, I want to stress it again. So this device model will provide, will include parameters such the parameters are twofold. One is IS beta. So beta will then determine the current ratio between collector and base. IS will then deliver the collector current. So this will then give you collector current, and through this ratio, through this, you will get base current. Right? This is one type of model which contains either this. So this is called the exponential model. So if you're using IS, then you're using the exponential. Let's go through an example of using the exponential model. So if I give you a circuit, I'm just going to give you a circuit. So if I'm giving you a circuit, it looks something like this. If we're using a bipolar junction transistor, the typical notation is to note it as Q. So that will be my device. For diode, you use D. For BJT, we use Q. For MOSFET, we use M. Okay? So Q would then stand for a bipolar junction transistor. This is an NPN transistor. We know it because this arrow is going down from the base. And then we're assuming that it's applying a voltage of 0.75 volts. Let me make sure I get the numbers right. An example. Okay, so we go 1K. Okay, so this is an example of using exponential model. So I'm having a simple resistor on top. So R1, and there will be a voltage. Okay. Let me just give you the convention once again. This is a common emitter structure. Remember, my emitter is grounded. So this is typically ground is typically referred as the common node, meaning that it does not carry any signals or biasing. Okay. So your most positive voltage is typically, we're using the convention of VCC. C stands for collector. Therefore, the VCC is because it's a BJT circuit. If we're using MOSFET, it will be VDD. So this is just a convention. And as I said, if you're using bipolar, you're using Q to indicate that it's a bipolar junction transistor. Okay? So once we have the circuit, I asked you to, wanted to find two things. One is that if this is my output terminal, so based on this model, so if we use a exponential model, So I give you two parameters, IS, which is 1 times minus 16. Make sure that I got it right. Oh. Okay, otherwise. So this is my device parameter. I'm giving you the IS and of course beta. In most of the textbook or example, we're giving you a number of 100 just for simple calculation. Okay, if this is the case, use exponential model, then it will ask you to find out what is the first, find out the collector current. Second, what is VO? Okay, so we're assuming that Q1 for Q1. So this device has an IS of 5 times 10 to the minus 16, and it has a common emitter current gain beta, which is 100. So based on the circuit, I forgot to give you, this is 1 k ohm. Based on exponential model, how does one approach this problem? So the problem is then fairly simple. You simply use the model to first find out collector current. The collector current, I'm sorry. Before we start, in this kind of analysis, you want to first make an assumption and come back to check whether your assumptions is true. So because there's different operating mode, so we're not sure whether Q1 is in active mode, right? You're not really sure. So you want to, typically what we do is that we make an assumption that it is, and then do the calculation and go back and check whether it fulfills this requirement. Okay? So based on this, I already know that my VBE is larger than 0, so it's 4 bias, but you're not really sure whether this is reversed. So we're going to check later whether this is reversed. You're going to check a little bit later, but now we assume. So first of all, you assume. We assume that Q1 is in active mode. Because it's in active mode, therefore I can use beta. Otherwise, you may not. So you have to make sure that it's in active mode first, and then IC will then be IS exponential. I need to find both terminals. IC, IB, and then 3 terminals. So first we find out collector. You start with finding out collector because we know the collector current equation right here. Okay? So this will be VBE divided by VT. Okay? So based on this number, you just simply plug in the numbers. This will be 5 times 10 to the 16th, 26 millivolts, 750 millivolts. Just want to make sure I got the numbers right. Okay. So once you plug in the number, this will be 1.7 milliamp. So first we established that our collector current is about 2 milliamp. This is, if you get a number in the range of milliamp or microamp, that will be typically correct. If you're getting a number of, say, 1 amp, that means that you definitely make a mistake somewhere or you set it up incorrectly. So milliamp is a typical operating condition for bipolar transistors. So then base current will then be IC divided by beta, which would then be 17 microamp, right? And then of course you can get emitter current by summing it up. So this will be 1.717 milliamp. Okay? So that's fairly straightforward. So the second part is then how do you do the find out output voltage. What is output voltage? Output voltage will be determined by how much current is coming through R1. So because we're not connecting output to any terminal yet, so then the current, your output voltage, part B, output voltage will simply be VCC minus ICR1. Right? Sorry, I forgot to give you, this is 3 volt. I said this is 3 volts, so that would be 3 volt minus IC, which is 1.7 milliamp, times 1 k ohm. Okay? So this would then give us our output voltage at 1.3 volt. So once we obtain our output voltage, you could go back and check whether our assumption is correct. Assume that Q1 is inactive. You go back and check whether it's true. So we go back and see what is VBC. VBC is 0.17 minus C. Collector voltage is now output voltage, so which is 1.3. So this is smaller than 1, so this is smaller than 0, which is in reverse. So we know that your BC junction is in reverse. So that validates our assumption. So the assumption is correct. Okay? So this needs to be done most of the time to make sure that whatever you're doing is actually within the range of your first proposal, first assumption, which is that Q1 is inactive. A lot of time you will probably get an answer which is not. Then you need these models are no longer valid. Okay. So once we have this understanding of how to use this exponential model, there's of course a simpler model. So if I wanted to actually give a complete large signal model, other than an exponential model, because you will see that if you're using an exponential model, it will actually complicate things. So if we wanted to do the same thing on a diode using a constant voltage model, then our circuit will look something more like this. So there's 2 ways of doing this, once again. Let me draw the exponential model. For exponential model, what happens is that your circuit, your equivalent circuit, will look something like this. This is collector, and I have a I want to establish an exponential model, as we said, other than this part. We already know that this part, you can use a voltage control current source with a model of IS exponential V, what is VBE or V1? I'll just make sure. Okay, VBE is fine. So I'm using VBE as my input. This is VBE. So it will be third terminal control collecting collector current through exponential model. This is the exponential model. And this would then be a diode with IS equals to, we typically refer this with an IS1, where IS1 is only beta times the IS given on the right. So there's a ratio between the two. Because PN junction is a 4-bias PN junction, so you can simply use a PN junction to describe it. The only difference is that it only contains whole current, the whole current part. Therefore, you're only taking out the whole current part. Therefore, this is the beta ratio. Okay, so this is how we model. We use an equivalent circuit to model a bipolar junction transistor, called large signal model. Of course, if you're simply wanting to find out your DC current bias level, the other model is we can also change our diode into a constant voltage model. If you're using a constant voltage model, then this diode would then be substituted by a So this is another way of analyzing your circuit through a simplified model. So the simplified model, simply assuming that the diode, rather than using exponential description of the current, you use VBE on. You're assuming that this is a constant voltage source. Okay, on the left-hand side, there's very little, and it will provide whatever current. The only difference is that it's current. So what determines this current? This current would then be a current-controlled current source. You use a CCCS to describe this. This will be beta times IB. Okay? And so in a constant voltage model, you simply assume whatever biasing on the diode will be a constant. It will be a constant bias across, typically close to 0.8, 0.7 volt, 0.7 to 0.8 volt. So in this class, we typically use VBE on for the operation region in milliamp. It's typically 0.8 volt. So I'm giving you a point voltage to describe the biasing condition between the two, and whatever you get out of this circuit, the base current will then determine your collector current based on this current ratio. Okay? So if you look at this, you think it's kind of weird, but we're just going to apply it to a case so that you get a sense. CCCS is a current control current source. This is a voltage control current source. VCCS. Voltage control, the other is current control. The third terminal current control the collector current. Base current control the collector current. Okay? So if you look at this model, it might look a little weird. So what we're going to do is just go through an example so you get a sense as when you can apply a constant voltage model, or how does one apply a constant voltage model in the circuit analysis. So we're just going to go through an example so you get a sense as to. Also a bipolar circuit example, this is VCC. We're still using a very commonly used common emitter structure, which is emitters connected to ground. So there's only one transistor, simple. And I also have a I'm using RC instead because I'm having collector N and base N. So connecting to the collector is noted as collector resistor RC, and connected to the base is RB. So this is the circuit that's being given to you. I'm just going to give the parameters for VCC equals to 2.5 volt. I have RC equals to 100 ohm. Base current is 10K. So let me just give the numbers. 2.5, 100 ohm. And then I have RB, which equals to 10K. Let me make sure I get the numbers right. Okay? So then, of course, we have the device parameter. So device parameter, instead of exponential model, we're going to use the constant voltage model, which would then give you VBE on and beta. So VBE on is 0.8 volt, beta is 100. So once these parameters are given, I will then ask you to find out, answer the same question is the terminal current. So I ask you to find out what is the collector base emitter current, the 3-terminal current. Okay? Of course, in these type of analysis, we typically want you to check whether your device is operating in the right mode. So you need to check this point. V, B, and A, sorry. So you also need to find out this terminal. using a different color. Collector node and also emitter node. So I want to find out your biasing voltage, which is the DC voltage on base and collector. Just to check whether your device are operating in the right mode. Okay? So the main difference between these two models is that if you're given the exponential model, typically what you want to do is that you want to establish what your collector current is through exponential model. But because now your collector current depends on base current, so we start on the base route. So if you start on the base route, because this is a constant voltage model, so it will simply tell you that your VBE, because I'm assuming constant voltage, therefore your VBE equals to VBE only. Right? So once you recognize that, you can actually answer this already. This equals to VBE only, so which is 0.8 volt. Okay? So once we establish that, we can find out what is its base current. So what is your base current? Your base current, I could actually write down the base current will simply be VCC minus VBE divided by RB. Right? Because my VCC, I already know this terminal, the voltage drop on RB should be established by the base current. So simply plug in the number, we get a current, which is, did I get it right? Or is it 2 point, yes, correct. Okay? So once you know your base current, then collector current is simple. Collector current is beta IB, which would then be 17 milliamp. This is fairly high. It's on the higher end of current level. So then you can also do the same thing. So your emitter current will then be 17.17 milliamp. So these are basically linked by this current relationship between the three. Okay? Among the three, I should say. So what is your collector bias? The same thing we need to do is that when we apply this model, we're assuming that Q1 is in, this is start with assuming Q1 is inactive. Okay? So you go back and check whether your collector voltage will support that. So we want to find out what your collector voltage is. So for the second part, VC will then be VCC minus ICRC. So VCC is 2.5. IC is 17 milliamp times 100. So it's fairly close. It's 1.7, so you get a voltage of 0.8. So that means it's at the border. Your VBC is 0, which is still counted as active because it's at the border. When it's slightly higher, then it would then reverse bias BC junction. This is 0.8. This is 0.8. It's already at the edge. Okay? That's good. So this exercise just allow us to, once we have this model, you can then get a sense as to how does one analyze its DC biasing condition. So look at these two examples. What we're finding is it's DC current, collector current, base current, emitter current. Also, it's DC bias voltage. So based on this. So next hour, I'm going to go into small signal analysis. So if I'm applying rather than a fixed voltage, I'm applying what happened. We're going to address the question is that what if I'm putting my signal onto the signal path? So in our next hour, we're going to talk about if I'm inserting a small signal here, what is the corresponding output modulation of signal. That's when the amplification happens. So it will become much more interesting once we have the small signal analysis model established, and then you could look at what happened if I'm having modulation input, how much amplification factor one can gain by having a transistor. Okay, good. So let's take a break for 10, and we'll come back to go into small signal analysis. So these are for large signal analysis is to give us DC voltage and current level. Current level are very important. The IC, the DC biasing current is useful to link small signal and large signal. And DC voltages allow us to check whether the device is operating in the right mode. Okay? Okay, let's take a break now.